This is a pre-built version of the application. So if we go ahead and run the server and two clients, and this will be the server, and this is the first client, and this the second one. And Alice will pick this number as her prime number P, and this one as her prime number Q, which is also a divisor of P minus 1, and this will be her subgroup generator alpha, and this one her private key D. And she calculates her public key beta and sends Bob her P, Q, alpha, and beta. And Bob receives those, and he will pick those values for his P, Q, alpha, and D, and he calculates his public key beta and sends his information to Alice. And let's say she wants to send this, and let's mention that we are running here in ASCII mode, since it is easier for testing. So in this mode, Alice and Bob will exchange ASCII hash messages. H of X. So let's say she picks this as her ephemeral key, and this will be her private key that she needs to enter, but let's have her enter a made-up key and see what happens. So here she calculated her signature param R, and here she is calculating her signature param S, and she is sending Bob her ASCII hash message H of X and her signature params R and S, and he receives those. So this is H of X that she sent, and he calculates W, U1, U2, and V, and determines that V is not congruent to R in mode Q, so the message was not signed with Alice's private key. So let's have her send the same message, but this time sign it with her private key. So we'll use the same ephemeral key, and this is her private key. So Bob receives her message this time and calculates W, U1, U2, and V, and validates that V is congruent to R in mode Q, so the message was signed with Alice's private key. And Eve here can see all the communications between Alice and Bob. So now she knows Alice's PQ, alpha, and beta, and Bob's PQ, alpha, and beta, and she can see the two messages sent from Alice to Bob. But in order to send the messages as being Alice, she needs to sign them, and in order to do that, she needs to obtain Alice's private key And to do that, she needs to solve this discrete logarithm problem, log base alpha of beta in mode p. And let's have Bob try to send this ASCII hash message to Alice, and have him choose this ephemeral key. So he calculates R, and his private key D was this number. So Alice receives his ASCII hash message and calculates W, U1, U2, and V, and determines that the message was signed with Bob's private key. Now, before proceeding with the code, let's do a quick summary and a proof. So Alice wants to send signed messages to Bob. So she starts by selecting a large prime number p between 2 to the 1023 and 2 to the 1024. And then she selects a prime divisor q of p minus 1, where q is between 2 to the 159 and 2 to the 160. But for the purpose of this tutorial, I used much smaller numbers for p and q. And third, Alice selects the subgroup generator alpha, and she selects her private key D between 0 and q, and she calculates her public key beta, which is congruent to alpha to the power of d in mode p, and she sends p, q, alpha, and beta to Bob. And now each time she wants to send a signed message to Bob, she selects an ephemeral key between 0 and q, and then she calculates R, which is congruent to alpha to the power of the ephemeral key in mode p, and all of that in mode q. And then she calculates S, which is congruent to the hash of the message X plus the private key D multiplied by the signature param R. And she multiplies all of that by the inverse of the ephemeral key, and all of that in mode Q. And she sends the message X and the signature params R and S to Bob. And Bob receives the signed message, and he calculates W, which is congruent to the inverse of S in mode Q. And second, he calculates U1, which is congruent to W multiplied by the hash of the message X in mode Q. And third, he calculates U2, which is congruent to W multiplied by R in mode Q. And fourth, he calculates V, which is congruent to alpha to the power of U1 multiplied by beta to the power of U2 in mode P, and all of that in mode Q. And he validates the signature by checking if V is congruent to R in mode Q. And if that's the case, then we have a valid signature. Otherwise, we have an invalid signature. And finally, let's prove that the signature RS satisfies this validation condition. So we want to start from here and arrive here. So this equation came from here. and this equation came from here. So we rearrange this equation, we obtain the ephemeral key is congruent to this, and then we have that W is congruent to this, and U1 is congruent to this, and U2 is congruent to this. So we use those here, and we get the ephemeral key is congruent to U1 plus D times U2 in mode Q. And we can raise alpha to either side of the equation and reduce mode P. So we get alpha to the ephemeral key in mode P, and alpha to U1 plus D U2 in mode P also. And we have that beta is congruent to alpha to the power of D in mode P. So we use that here. And finally we reduce both sides of the equation in mode Q. And this turns out to be R from here. And this turns out to be V from here. So we get R is congruent to V in mode Q. I will start by creating a new project. And here we need to do JSON. So let's pick up this jar from here. And we go to properties and Java build path. And here we will have two packages. One for the server code and another one for the client code. And on the server side we will have two classes, a server class with a main method and a server thread class, and on the client side we also will have two classes, a client class with a main method and a client thread class. And both client thread and the server thread classes will extend from thread, and we will start work on the server side. And this class will have three instance variables, a server and a buffered reader and a print writer. And the constructor takes in a socket and a server instance and uses the socket to initialize the buffered reader, and the print writer. And the server will be listening on this port, and we'll have two instance variables, a server socket and a set of server threads. And we'll use the server socket in order to accept client connections and dedicate a server thread instance for each one of those connections, and then add that server thread instance to the set of server threads, and call the start method on the thread, which will end up triggering a call to this run method when the operating system decides to do so. And let's add this method here that uses the print writer to forward the messages, and it will be called from here to forward the messages from Alice to Bob, or the other way around. And this is just a get method. And here, when a message comes in, as a JSON object, we check if that message contains the public key for Alice or Bob, and we display what that key is, so P, Q, alpha, and beta. And then if that message contains h of x, then we indicate that Eve needs to solve this discrete logarithm problem for Alice or for Bob in order to sign messages as being Alice or as being Bob. So this should do it for the server code. And here we will keep track of this client name and P and Q and alpha, and the private key D, and the public key beta. And we will also keep track of the other party name, P, Q, alpha, and beta. And this flag indicates if we are running in ASCII mode, and this one if we are ready to send and receive messages. And we will have this is ready flag method, and those get and set methods. And this static method checks if a number is prime, and this one hashes the message given a hashing algorithm. So the hash ends up being signed and verified and not the message itself. So here we pick up the hashing algorithm message digest instance, and then we add the bytes of the message to the message digest, and then we call digest to get the bytes for the hash, and here we encode the byte data to hexadecimal format, and then we append it to the string buffer instance we have. And here we keep track of two instance variables that we initialize from the constructor, which takes in a socket and a client instance, and we use the socket to initialize the buffer reader, and we will have this method that handles sending messages from this client to the other client, signed messages, and here we first check if we are running in ASCII mode, and we display that message in that case. And for the purpose of this tutorial, the server will be running in localhost and listening on this port. And we instantiate a client thread which will handle receiving messages from the server, and we call the start method on it, which will end up triggering a call to this run method when the operating system decides to do so. And this method handles the setup phase. So it prompts the user for the name and for the prime number p and the prime number q, which is a divisor of p minus 1, and the generator alpha, and his private key D. And it calculates the public key beta, and it puts the name and P and Q and alpha and beta in a JSON object and sends them to the other party. So in the communicate method, we first make sure that we handled the setup phase. So we stay in this always true loop until this has been handled. And we need a method that does the pickup of the message and hashes it and signs it and sends it across. So this method does all that, and we call it to send the messages from this always true loop. And we need two methods, one to handle the pickup of the ephemeral key, so it prompts the user for that, and another one to handle the pickup of the signing key, and it also prompts the user for that. And this method handles the hashing of the message. So here we are using SHA-256, and we only hash the message if we are not in ASCII mode. Otherwise, we assume that the user has entered h of x, so the hash instead of the message, since easier for testing. And here we first pick up the message from the user, and then we call the handle message hashing to hash it. And for the purpose of this tutorial, I had the user enter the ephemeral key, and this method takes in the ephemeral key and use it to calculate the signature param R. So this is how we calculate R. R is congruent to alpha to the power of the ephemeral key in mode P, and all of that in mode Q. And we call this method from here. And this method calculates the signature param S, so here we pick up the signing key, and this is how we calculate S. And this method sends the signed message, so X, and the two signature params R and S, and we call those two methods from here. So this should do it for this class. And here we need this method to receive the other party P, Q, alpha, and beta, and we end up calling it from this always true loop. Otherwise, if we are receiving a signed message, then we handle it here. Now this method obtains the message hash. So this is the value of X, and we are using SHA-256 to hash the message and return it. And we need those two helper methods. This one displays calculations for W and U1 and U2 and V. And this one validates the message and indicates if the message is valid. So V is congruent to R in mode Q. Otherwise, if the message is not valid, so it was not signed with the other party private key. And this method handles receiving the message. So here we calculate W, U1, U2 and V. And we display the calculations and validate the message. And we end up calling this method from here. And here we obtain the message hash. So this should do it for this class. And let's go here and change this and make it default to false. And let's update this one. Need a plus here. And finally, let's go ahead and test run the application. So we'll have a server and two clients. And this will be the server, and this the first client, and this one the second one. And Alice will use this number as her prime number P, and this one as her prime number Q, which is also a divisor of P minus 1, and this will be her subgroup generator alpha, and this one her private key D. And she calculates her public key beta and sends P, Q, alpha and beta to Bob, and he will receive those. And picks those numbers as his P, Q, alpha and D, and he calculates his public key beta and sends his information to Alice, P, Q, alpha and beta. So let's say Alice wants to send this message to Bob, signed message. So she calculates the hash for the message, and for the ephemeral key, let's say she picks this number, and she calculates the signature param R, and for D, let's go ahead and pick a made up key for now. So it should be this number, but let's go with this number and see what happens. So she calculates S, the other signature param, and sends her information or her signed message to Bob. So X, R, and S. And he receives those and calculates the hash for the message, and notice that the two hashes are the same. And he calculates W, U1, U2, and V, and determines that V is not congruent to R in mode Q. So the message was not signed with Alice's private key. So let's go ahead and have Alice send the same message, but this time sign it with her private key. So we'll use the same ephemeral key, and this time we'll use her private key. So she does the same thing. She calculates the signature param S and sends her signed message to Bob, and he receives that and calculates the hash for the message, and then calculate W, U1, U2, and V, and validates that V is congruent to R in mode Q. So the message was signed with Alice's private key. And Eve can see all the communications, so she knows now Alice's PQ alpha and beta and Bob's PQ alpha and beta, and she can see the messages sent from Alice to Bob. But in order to sign messages as being Alice, she needs to obtain Alice's private key, D, and to do that she needs to solve this discrete logarithm problem. Log base alpha of beta in mode P. And let's have Bob send this message to Alice, and maybe choose this ephemeral key. And this was Bob's private key D. So he calculates S and sends his signed message to Alice, and she does the same thing, receives it, calculates the hash, and then calculates W, U1, U2, and V, and determines that V is congruent to R in mode Q, so the message was signed with Bob's private key.